Hi, welcome to NOAA Live. My name is Nicole Bartlett, and I'm going to be moderating today's webinar. This series is sponsored by NOAA's Regional Collaboration Network, where I work, which is spread across the country and helps connect people to all that NOAA does. It's also sponsored by Woods Hole Sea Grant, located at the Woods Hole Oceanographic Institution here on Cape Cod, Massachusetts. NOAA Live webinars are being offered most Wednesdays during the school year at 4 p.m. Eastern Time. To get more information, visit the Woods Hole Sea Grant Education webpage or just follow them on Facebook. This series is designed to help you get to know NOAA and some of our incredible experts. All of our speakers work for some part of NOAA, the National Oceanic and Atmospheric Administration. Today, we're introducing you to Tim Walsh with NOAA's satellite service in Silver Spring, Maryland. Well, we'll be talking about NOAA's role in satellites and satellite architecture. We want to recognize that we're all coming to you from the traditional lands of Native communities who have substantial traditional and local knowledge and much to share with us. We acknowledge that Tim is coming to us from the land of the Piscataway Conoy tribe and the Piscataway Indian Nation. We're hosting this webinar from the ancestral lands of the Mashpee Wampanoag tribe and the Wampanoag tribe of Gayhead Equina. A few guidelines before I hand you over to our speaker. You're all muted because we have a lot of people on the line and want to make sure everyone can hear our speaker. However, there's a box where you can write questions. It's where you told me you were calling in from. Please let us know if you're a class tuning in, and if there are multiple people watching that class, let us know who's asking the question. We encourage you to ask as we go, and Tim will stop periodically and answer a few questions. We may not get to all of them, but Tim and the folks at the satellite service promise me that they're going to answer all your questions, whether it's in the webinar today or after the fact. Is that right, Tim?
Absolutely, definitely.
Okay. All right. Well, I'm going to turn them over to you.
Thank you so much, Nicole. I'm really excited to talk to you all today, virtually and otherwise. Nicole mentioned that the National Oceanic and Atmospheric Administration is our name. The thing people don't often realize is that we also are in space. And so we use space to actually look at the atmosphere and the ocean from the space vantage point. That's what I'm going to be talking about today. I'm going to start out by talking a little bit about myself and how I got here, because it's amazing how life takes you. But I started thinking about space back in 1969. Now that tells you a little bit about my age, but I was 4. And I got so excited it was my first television memory, actually, when Neil Armstrong and Buzz Aldrin stepped on the moon. And I knew at that time, at age 4, that I wanted to do something in space. Now, I wasn't quite an astronaut, but I was able to start working in that direction. As I grew up a little bit over the next couple of years, I got really sucked into science, all things science and science fiction. A lot of you know Star Trek and Star Wars and things like that. I really got pulled into, I kind of figured that someday I'd want to live in space. So again, I didn't quite get there, but I wanted to get involved and start studying those things that would get me to this kind of work. So as I got a little older, I started building some model rockets. Now, some people might recognize model rocketry, but I started building the kits, and then I started deviating and building things on my own and figuring out things that worked and didn't work. It's about discovery, and that's kind of what engineering is all about, which is solving problems using math and science. And that's kind of what I was doing starting out. I didn't realize it at the time, model rocketry. I went to school to be an engineer, and then I came out with an electrical engineering degree, but I started working at NASA saying, what can I do to get involved with this kind of work that seems so cool? And I got involved with satellites, and specifically weather satellites. And our customer at that time was NOAA. So NOAA and NASA have a very close collaboration that goes over many years in this kind of business. And so I started working with the development, building, testing, and launching of these satellites. And the satellite in the lower left-hand corner is an example of one I worked on. And then this particular launch is one that's just a couple of years ago, and it was kind of an exciting one. This is the one that was launched it was at the Kennedy Space Center in Florida. And it is now actually a satellite that's perched over the west coast of the United States. It can see all the way from Australia and New Zealand, all the way over to the middle of the country, but it has Hawaii kind of right in its center, and Alaska too. So we really get a good vantage point of the western part of the Western Hemisphere. So what's so special about being in orbit? And what can we see there in space? And what can we do to help the people the meteorologists, the people that look at the data and figure out what our weather forecasts look like? So we're going to talk a little bit about that. And by doing that, we use a couple different orbits that are really special, that give us a unique vantage point that help us with those particular observations. And so I'm going to describe just two today. You can think of them as the big orbit and the little orbit. The big orbit is something we call geostationary orbit. It's an orbit that's right on the equator, and I'll go to the next slide. This one that's kind of horizontal is the geostationary orbit. It orbits once per day. It's a very special orbit because from the vantage point of the ground, it looks like the satellite is not moving. And that's really unique because it can always be staring at one spot in the Earth at all times. And that kind of gives us that kind of high definition video that you see when you look at a hurricane or something like that. So it helps us with severe weather. It's always looking at one part of the Earth. The other ones that are more horizontal are low Earth orbiting satellites. We call them LEO. And those satellites are just about 500 miles off the Earth, and they're zipping around the Earth 14 times a day. But the unique thing that they have that the geostationary one doesn't is that it looks at the whole Earth. I'll give you an example of that here. First, to give you a sense of scale. If you're in the lower right-hand corner here, if you see my cursor, if you're on a jet aircraft, you're probably a couple miles off the Earth. If you're an astronaut in the ISS, you're about 250 miles off the Earth. If you're on one of our satellites, you're a little bit farther up. You're up around here, 500 miles. A lot of you use GPS for various things. Everyone, GPS is omnipresent. So that's a middle Earth orbit or medium Earth orbit. And then we talked about this high Earth orbit, or what we call geostationary. This video here kind of gives you a sense of what the low Earth orbit does when we look at the Earth. This would be a course of 14 different orbits, and you look at it, the green is kind of the data, a ribbon of data that we're collecting from space. And if you look at it, over the course of a day, we cover the whole Earth twice. That's really valuable. And then we have to bring that data down from the satellite to the Earth. And we do that because it flies over the two poles. We have two ground stations, one at the North Pole. It's actually on an island called Svalbard Island, north of Norway. And then we have another one down at McMurdo Station, which is in Antarctica. And it's two pretty tough places to survive, not to survive, but they're very severe environments, but we work it out. And we basically have, this is an example of a picture of the Svalbard Station where they have over 100 different antennas, a couple of which we use to bring down that weather data. But it's interesting because right now this area is completely in darkness. And if you were to go to one of these antennas, you have to bring all your tools with you, but you'd also have to be worried a little bit about polar bears, which are on the island. And then down in Antarctica, this is a McMurdo Station, which is a big research station, but we have a number of antennas down there as well. Once we get all that data, we bring it to a central spot. This is the same building that we control all the satellites. We basically talk to them. We send them commands and we get data back from them. And this is in Suitland, Maryland. It's in the Washington, D.C. area. And it's a building that it's kind of a unique building to look at, but this is where all the action is. And finally, I did want to say in this, before we take a pause for some questions, is we work with a lot of international partners as we get the data for these models for forecasting, including the Europeans, the Japanese, and a lot of other, even the Department of Defense, other organizations that have satellites that also collect data from orbit. And what we do is we take all this data and we put it into a mathematical model that basically takes what the Earth looks like right now and predicts what it will look like in the future. That's called a weather forecast. And so on the right there, you see something like a 7-day outlook. Sometimes they have short-term outlooks, or short-term forecasts, what it might look like in the next 6 hours or 1 day. Sometimes they might extend quite a bit. But a lot of the data that's used for this modeling is coming from these specific satellites. I'm going to pause there. I know that's a lot of information, so I wanted to give you guys an opportunity to ask any questions.
Okay, Tim, we do have a couple of questions. So can you go back to the picture of Svalbard? Let's see.
Yep.
So I think this is the one Zach is asking about. He wants to know if those are runways for planes.
Great question. It's interesting because that is a big plateau, a big flat plateau. But I've had the opportunity to fly into Svalbard, and there is a runway that's way to the left of this. But this is a plateau that's a nice head. Doesn't have, it's above the mountain ranges, so you can see a lot of the. It's a clear view to the sky. But those roads that you see there are literally just roads that they use to service the antennas. Now, the question you might have is, why do they have balls? Why do they look like little golf balls on there? Well, they're basically wind. They protect these actual antennas from wind because it gets very windy on these plateaus. And so the antenna itself looks a little bit like a bird, like a bird bath. It's basically an inverted dish, and it follows the satellite as it goes across the sky. But it's not a runway, but it is a road. That's what those are.
Okay, great. That's a good question, Zach. Casey wants to know how many people work there. And that looks like a building right in the middle, right? So how many people are supporting this?
In Svalbard, well, that's an excellent question because it is definitely a place that you have to be committed to work there because there's a town close by that has a couple thousand people, but it's not a huge city. And I think if you were to go to work there, you have to be committed to work there for a period of time because it's not an easy place to get to, quite honestly. And so I do know that when we visited the station in Svalbard, there were, a couple hundred people that would support the company that's doing the work here, but there were literally just a couple dozen people in the control center at the time. So it is largely automated, but it is impressive. I mean, I definitely have a lot of respect for the people that work there and the people that are committed to doing the mission that we need there. Great question.
I'm actually surprised that several hundred people work there.
Well, I will say that it's more like I will say they work for that company, and part of the company is in Norway, and so they actually are kind of shuttling between the two.
Gotcha. Okay, Jaden has a question. He wants to know, did the satellites all go around the Earth the same way?
No, they don't, and that's a really good question. They go in these different orbits are basically, think of them as a path around the Earth. And an orbit is nothing more than a satellite falling towards the Earth, but it's moving so fast that it misses the Earth. It sounds kind of odd, but that's what an orbit really is. And so the satellites, and I'm going to go back to real quickly to the picture.
Perfect. I was just going to suggest that. Thank you.
Yeah, and I described those two orbits, and I would really like to describe orbital dynamics to you folks, but that would take a long time. But really, just think about the two unique orbits I identified. One of which was that one that's way out there called geostationary, and that's used for staring. And the LEO orbit, or low Earth orbit, is used for full global coverage, and that one is really important as well. So together, they form kind of that complementary set of data that we need to predict the weather.
So, but we don't have other satellites in the low Earth orbit going in the opposite direction, or do we?
We don't. Well, there's so, if I showed you a picture of all the satellites around the world, you'd be amazed. It looks like a bunch of bees around a hive, but they are in all sorts of orbits for different applications. Like satellite orbits are used for communications, for internet communications, and things like that. But these are the ones that we use. And that's a great question because the LEO ones are usually polar orbiting for weather applications. There's a long-winded reason for that, but it's basically to keep the sun's perspective with the satellite. It's basically the same solar angle, which, to make a long story short, gives a similar perspective for the weather forecasts as they go around the Earth.
Gotcha. Okay, one final question about the ground stations. Maybe you can pull up the Antarctica one while I ask you this one. Let's see, Ferris is asking, is it a 24/7 operation at these ground stations? And do folks work like 8-hour shifts?
Yes. First of all, it is nonstop, 24/7, 365, and we do have people. Different groups work different shifts. We actually at NOAA we use a lot of 12-hour shifts, and so people will work 12 hours on, 12 hours off. But different stations will do different things. But yes, it is around the clock. These satellites never stop, and the data is always constant. And I'll describe it later when we're talking about the satellites. But we have to take imagery when we have to take pictures of the Earth during the day and at night, which is unique.
Okay, I knew this question was going to come up, Tim. So yeah, I have to ask it now since Joseph asked. Has a satellite ever hit another satellite?
Well, the short answer is yes, and it's something that we're going to continually have to worry about. We try to keep an eye on all the satellites that are around us, and sometimes we actually have to move the orbit of our satellites to try to avoid the probability or reduce the probability of us impacting another satellite. It is a fantastic question, and I hope somebody that's listening here can try to think of ways to reduce this from being an issue in the future. It's going to be something that we're going to, as more satellites get into orbit, it's going to be something that's going to be more and more important. But yes, there was a satellite that impacted another a couple of years ago.
All right, that's great questions, guys. That's a good place to let you continue.
Yeah, okay. So I'll start by saying that the teams that we utilize to do this are really, first of all, they're integrated NASA NOAA teams. We have a long history working with NASA. And we're all across the country. I heard some people on this call are from Colorado and from Arizona. One of our satellites is built in Gilbert, Arizona, and one of our satellites is built in Littleton, Colorado. And so we have a lot of, those are where the satellites are built, and our instruments are built all across the country. And then we manage them here from the DC area. So there's a lot of things going on. Normally we travel a lot. Now we're doing a lot of Teams or Zoom type calls. I'm just showing you this picture because this is my last program, and I think you'll notice that there's a unique guy over here that's looking like a hot dog. That's not me, but I'm the one right behind him. So this is an easy picture for me to use when I'm trying to identify where I am in the group. But it's always, the fun part is it's a fun integrated group, and it's people that are very passionate about what they do. Just to give you a little bit of sense of the size of these beasts, they're big satellites, so looking at the top 3 satellites on the left, those are 3 satellites that we, NASA, NOAA, have built and have launched. And you'll get a sense on the right as to how big they are. They're humongous. And humongous usually means expensive, because getting something that big off the ground takes a big rocket, and those are expensive. What we're trying to do is reduce the size through miniaturization over time. This gives you a good example of what a satellite looks like relative to a person. Now, this is a satellite that looks like it would be on orbit. Usually, when we're on the ground, we're buttoned up and ready for launch, and things are not kind of all out like this. But you get a sense of how large these things are. This is the satellite I currently work on. It's the shirt that I'm wearing. It's the Joint Polar Satellite System, and it's also a NASA NOAA effort. And we're launching next year. We're getting excited about a late next year launch. We have 2 of these in orbit right now, and this is an example of one of ours that's in orbit. Here's a picture of that, actually, the satellite that was launched 3 years ago. And it's actually a picture of we call it a high bay, but it's a building or room the size of like a gymnasium. And it's in an ultra clean environment. The air is ultra purified. People who are in there are all dressed in the clean room suits. They call them bunny suits sometimes. But here's an example of what the side of the satellite that's always pointed at the Earth. So all the instruments are on one side. And what you see here on the right is something we call an imager, but it's what takes the photos of the Earth. And then we have instruments that measure temperature and humidity. And then there's also instruments that measure effects of solar radiation. So that might help you when you're figuring out what an ultraviolet forecast is, and when people need to worry about covering themselves up in the summertime. So the fun part, and this is an example of what you might see in one of those buildings in Colorado or Arizona where we put these satellites together. But in the lower left-hand corner is a picture of one of the instruments arriving at the facility that the satellite is being built. And then we put it all together. And then you'll see it on the right-hand side is a bunch of technicians getting the satellite ready to be tested. Now, when I say tested, we have to really put it through its paces. We have to make sure these things are going to last 5, 10, 15 years on orbit. So we have to make sure that they're fully tested and they're ready to go. And more importantly, when they get launched, they're put through a really rocky ride on a rocket. So you have to make sure that nothing will fall off of it or otherwise break. I know that's a lot too, so I'm sure you guys have some great questions now.
All right, yes, we do have a question, a good one that came in just now. If you back up once, Becky wants to know, did you say why everybody's wearing robes and slippers?
I alluded to it, but I should go into it. all of these, when you go to work at a facility like this, you don't want anything that you might be carrying from home, like whether it's some dog hair from your pet or dust from just the trip on the way to work. So we put these suits on, and depending on the type of satellite, you'll see even more covered up than others. But we have face coverings, we have hair coverings, so you don't want any hair falling off, or any type of particle falling onto the satellite. Now you might ask why. Well, we have these really incredible, basically cameras on the satellite, and you don't want any dust or anything to go on the optical surfaces of these instruments, because you want them to last for 15 years. And so that's why we keep ourselves ultra clean, and that's so critical. And so yeah, that's why you see all this. I referred to it earlier as a bunny suit. Sometimes you see people, they look like bunnies.
That's a good, so you guys remember that bunny suit. You can sound like you know somebody who builds satellites.
Right.
So another Becky asks, what's the foil material on all the satellites and the instruments?
Also a very good question is that when we get on orbit, I refer to it as a kind of an unforgiving environment. You're in a vacuum, first of all, and then because you're in a vacuum, when you're exposed to the sun or to when you're behind the Earth in the shade, the thermal environments can get very, very extreme. Like you might get super hot in the sun and they get super cold in the shade. And so what we do is we put these thermal blankets on that, depending on the part of the satellite, will either reject heat or retain heat, and try to keep the temperature of what's inside the satellite at a more reasonable temperature. So that's a really good question, because these are called thermal blankets, and they're used to either reflect sunlight. A lot of them are reflective. Sometimes you see black, which is absorbing solar radiation. So it's used to maintain the temperature of the inner parts of the satellite.
Great. I have one other question I wanted to ask now. Aiden in Germany wants to know, how do you build the satellite? I mean, how do you know what goes on and what goes where, and how is it assembled?
Well, we have people that I started out in what's called systems engineering. So the first thing you want to do when you build a satellite is, well, first you work with the scientists, you figure out what kind of instruments you need, and then you have to define these interfaces, because these instruments might be built all across the country, and in some cases the world, because we have got some instruments from Europe as well. But they all have to come together and fit. That's a really good point, is they have to fit properly. You don't want to have to redefine, we call it an interface. So you basically have to get together, define what a satellite looks like, and then how an instrument would fit onto that satellite, so that when it does arrive, that it is all the holes line up and all the connectors work and all that sort of stuff. So that's what's called systems engineering. The systems engineers define the interfaces for the satellite and make sure that everything fits when it comes together.
Wow, that's really cool. So It's kind of like a Lego instruction booklet, just sort of walks you through.
That's a great analogy. Yes, you want to make sure that the blocks all fit.
Yeah, great. Okay, I'm going to ask Michelle and Joseph to hold with their questions. They want to talk about what happens if parts come off and how you launch the satellite. So I know you're going to get to some of that, so I'm going to hold that for a little bit longer.
Okay, well, yeah, that's a great lead in, because we're preparing for launch. Now that we've built the satellite, we've tested it, we've put it through its paces, we're ready for launch. The first thing we do is we fly it or truck it to either to California, where Vandenberg Air Force Base, about 2.5 hours north of LA, is where we launch some of our satellites, and then or down to Kennedy Space Center down in Florida. This particular location is the last JPSS satellite that we launched, and this is from Vandenberg. And what you see there is a protective covering that protects the satellite from the aerodynamic forces or just the air forces on the satellite as the rocket is pushing it through the atmosphere. That's really critical, because you can't have, as you pointed out, you can't have things falling off. And if you did not have this protective, it's like a clamshell. And so when it's in the atmosphere, it's still there. And then when we get above the atmosphere, we pull it off, and then we let the satellite go. But that's what we use. And then we bring it out to the launch pad, and it's already in that protective covering. And we literally, as you can see on the right, we kind of raise it up to the top of the rocket, place it on top of the rocket. And then there's a whole separate group of engineers that are focused on the launch vehicle itself. Now that's really cool stuff. I deal with the satellites. We work with a whole bunch of people that deal with rockets, but can't do one without the other. They're both important. And here's a beautiful picture of our last rocket, right the night before the launch, which is a middle of the night launch. And I'll give you a little bit of a sense of what that looked like here. But this occurred early in the morning. This is a rocket called the Delta II rocket. And you can see a bunch of those tubes on the side. Those are solid rocket booster engines. They're extra engines that are used to give it some extra oomph to get off the ground. And so we basically will use that to get to orbit. And I'm going to speed up just a little bit here. Okay, here's a little bit of an animation that will show when we first launched, there are 8 of those tubes on the sides that are supporting they're augmenting the main thruster. And 6 of them will fall off shortly, and then 2 will be remaining. And then I won't go into all the stages, but a rocket is usually a number of different stages, which is basically pieces of the rocket will fall off as they finish doing their job, like there's the solid rocket motors are being let go. And then as we go forward in time, let's go a little bit faster, you can see that this is the upper stage of the rocket. It still, as you notice, has that clamshell on the top. Now here it comes apart and you can see the satellite. Now this is the key. This is the whole, we're almost in orbit here. When we get to orbit for one of these LEO spacecraft, we're at about 14,000 miles an hour, so we're moving. But it has to be pushing us in the right orbit in the right direction. So that's what the rocket does. It gives you the ride. And so that's what what we're seeing here. And I'm going to get to a really quick point here. This is where we call separation. And that's where the business of the rocket is, they've done their job. And that's where we do a lot of high fives and stuff like that. But then now the satellite itself has to be put through its paces. It has to be turned on and tested. I'm going to talk a little bit more about what you see here a little bit later. But I bet you there's a couple questions about what it takes to launch a rocket. So I'll
Good guess, Tim. We have a couple of questions. Well, I didn't ask specifically about testing. So how do you test the satellite? Are you going to talk about that next, or can you answer that now?
No, I can answer that now, because that's the first thing we have to do when we get on orbit is that big solar panel. And I have a model here that I can show you. Here's a picture of one of the satellites. When we launch, this panel is folded up against the spacecraft. And when we get to on orbit, this panel here, this blue panel, it actually takes solar energy and makes electrical energy out of it. So it's a solar array is what we call it. It's 2 solar panels. And so we need that to be deployed or unfolded. And so that's really critical so that we can actually get power to things. And then what we do is we start turning on critical elements in the satellite. We even turn on instruments, and then it takes a couple months to fully check out all the instruments on a satellite. And then there's a special date when we say, okay, everything's looking good, everything's fully tested, everything meets requirements. We have to measure things to make sure they're proper. And then we tell our customers, like the National Weather Service and the other people, that we're ready to go. So it's about a multiple month job to get there.
Wow, months. I had no idea.
Yeah. Well, the last years after that, but yes, it's a couple months after. You want to make sure it's just right. It's almost like sailing a sailboat. You have to trim the sails and make sure everything's proper. And there's a lot of things you have to adjust.
And I think you could also mention the redundancy that we have. So, unless this is a brand new satellite, you might want to talk about that.
Sure. It's funny, when I was in high school, I worked in a car garage. And so working on cars was easy to do because when things break, you bring them in and you fix the cars. In space, you can't do that. You launch things and you've invested so much money into it that you want it to last for 15 years, 5, 10, 15 years. And when things break, and they do, because it's a very harsh environment, you need to be able to solve the problem from afar. You can do it sometimes with software. You can do it with redundant hardware. And when I say redundant hardware, you might have 2 heaters for every part. So for something that needs to be heated up, you might have to have 2 elements for every part. So there's a couple, or whether it's power components or data interfaces, you want to have a replicated version of it so that if something goes wrong, that you can switch to a backup site. It's like having a backup computer on your satellite.
Sorry about the typing. I apologize. I was just responding to somebody. So Joseph wants to know, has a satellite ever failed to open the solar panels in space?
I will say absolutely. There have been some very bad days for people that have had to launch and check out satellites. I'm lucky to say that in my history that we haven't had that problem. But that's why we test things so much on the ground. We actually will do tests, or we call them mechanical deployment tests. Make sure that the solar arrays unfold. But yes, that has happened before where arrays will not unfold, and that's a very sad day.
Oh, I believe it. Let's see. Oh, Mylene wants to know, and I had a feeling this question was going to come up. What happens to the stuff that falls off? So does it fall back down to Earth, or does it stay in space and just float around?
And my answer is that it depends. It really, if it's low enough, most of it will fall right back into the atmosphere. Fortunately, is moving fast enough that it'll just burn up and nothing will ever hit the ground. So it's a great question though, because there's some things, like an upper stage for a rocket, where it's so far out of the atmosphere that it will keep orbiting. And so what they do is they actually retain enough fuel on that upper stage of the rocket so that they return it to Earth so that it will burn up and not kind of litter the orbital environment. But that's another part of that problem that we were talking about earlier, which is you want to keep stuff from cluttering up that environment that we're trying to operate these spacecraft.
And one final question before we move on, which I think this is a great question for you, Tim. Jaden wants to know, how many satellites do you launch in a year?
Do we launch in a year? So it's, worldwide, literally there are hundreds. I don't know if anybody has seen there's a satellite company or a rocket company called SpaceX, but they launched the Falcon 9 rocket and some other rockets, but they recently have been launching satellites 80 at a time, which is phenomenal. But these are tiny satellites, and we're going to talk about those in a little bit, but they're launching now hundreds of satellites, literally it's mostly for internet access and for communications. But that's where NOAA will launch one every other year, roughly, because we don't need to launch them a lot. We have our specific requirements that we can meet with just a couple launches every couple of years. And so it's not necessarily for us how many we're launching, but if you look at all over the country, or all over the world, I should say, how many satellites are being launched, you'd be amazed. There's a lot of great websites that maybe we'll add to the notes for this presentation that you could check easily online as to what's being launched.
Perfect. I'm going to let you continue there, Tim. Thank you.
Okay, so I'm going to quickly say a couple words as to what we see from on orbit, which I admit I'm an engineer, not a scientist, but I love talking to the scientists because they're always asking us for better equipment, better instruments, and better data. So we see snow and ice. Fire and smoke is a surprise to me. I didn't know that we would be looking at fire and smoke, but we can often see fires before people see them on the ground. And if people are in California, you know that this has been a really tough year for California and fires. Lightning and other clouds give us a lot of pre-indications for severe weather like hurricanes and tornadoes. And we even look at the sun. So I won't talk about the sun here, but I understand that there was a NOAA Live discussion about solar weather. And that's a really fascinating field but basically all I'm going to say is that a lot of the Earth's weather is really driven by the sun. It really starts with the sun. I'm going to give you two short examples of some events that have happened that satellites have helped with. The one is based up in Alaska. There's the Yukon River is in the lower right-hand corner. You can see what it would look like, this black ribbon here. And there's a town, Galena here, that in May of 2013, there was an ice jam at the end of the winter when all the ice is breaking up. Sometimes it'll jam up and can cause flooding upstream. It's exactly what happened here. And this is an example of some of the LEO spacecraft used to help define the extent of the flooding damage and try to give people some advanced warnings. And then some of the other things that people see that are probably more familiar with is this was a tremendous year for hurricanes in the United States on the East Coast of the United States specifically, and particularly in the Gulf. You know, there were a lot of landfalls of a lot of hurricanes. And so this is an example of Hurricane Laura in August of this year, and some pretty tremendous damage. But more importantly, what this data gives us is a sense of where the hurricane is going. And so it could get people evacuated from coast and kind of save lives and property. And that's the key for us. And some questions there about the data.
We do have one question. So from Ferris, he wants to know, how does the data become usable after you do all the testing? Like, how does it, how do we start?
I love that question because, you know, we get the data off the satellite. We call it like raw data. It's basically unique to that instrument, that spacecraft. And so what we do is we take it on the ground and we basically have to make it usable for these models I was talking about. And those models might be accepting data from multiple types of satellites, and European satellites and US satellites and others. And so we basically have to calibrate it. We basically make sure that it's, you know, a 10-degree measurement is a 10-degree measurement across the board. In other words, you want to make sure that things are being properly measured. And sometimes we do that by having onboard measurements of things that we know, and then things that we can compare the data to. And so basically we calibrate it and navigate it. And I say navigate it, we make sure that we're looking at we know exactly where it's looked at, where it is on the ground, so that we can make sure that people are being warned in the right spot for a storm that's coming, things like that. But it is a really good question. Without going into great detail, I would say that that's where a lot of the excitement is, because you got to take all this raw data and make it usable very quickly for the meteorologists that are using it.
Great. Let's see. I think you mentioned this, but Julian just is clarifying. Do the satellites dump their data each time they pass the pole? So it's Svalbard and McMurdo?
Yes, and so 14 times a day means that an orbit takes 90 minutes. And so we don't want to wait 90 minutes for the last bit of data. So we actually get them every 45 minutes. In other words, a half orbit, we see it at the North Pole, and then a half orbit later, we see it on the South Pole. And so we get that data every 45 minutes, and it's immediately sent to the people that are processing it and then putting it into the models.
And then a final question, Katya asks, can the satellites communicate with each other?
I'm going to show, if you're okay, I'm going to forward to another picture to help with that. So we're going to talk a little bit about the future. And I talked about these big monster satellites, right? They're the size of trucks. And in the future, we want to do a couple things. We want them to get smaller, because smaller means cheaper and maybe easier to replicate and get up there. And it means the more of them we have up there, the faster we can see things and get the data to the ground. And to go to the question that you just mentioned, if these satellites can talk to each other, the satellite that's above the ground station that can receive the data can get the data from other satellites that are not above that station. So in other words, the answer is absolutely. We want them to be able to talk together. Currently, the ones that we have up there are only talking to the ground, but we want to have what's called satellite crosslinks, which will give the satellites the ability to interact with each other. But that's a fantastic question. But these particular satellites that you're seeing here is what we'd like to do is go from the size of trucks down to the size of like a loaf of bread. I think on that image that we saw earlier, it was like the size of a watermelon. But what you see here is literally like the shape of a loaf of bread, and it's about 10, 20 pounds max. You know, so it's small. So that means that the objective is to try to miniaturize some of the instruments that are getting the data for us. And you might not put as much redundancy on there. Like in other words, you might be able to accept a little bit more failure because you have more satellites on orbit, if that makes sense. So that's something that we have to keep an eye on. The other thing we want to do is take these little satellites and make them so you can plug and play a number of different types of instruments on it. This is an example of a NASA constellation. When I say constellation, I mean grouping of satellites that have a similar satellite, but with a different instrument giving different data. And that data works together. So it's kind of the direction we want to go. And this final animation here gives you a sense of what I'm talking about, is that these satellites are so small that they can be distributed like peas from a pod. Like we can, you might have a larger satellite and you might hitch a ride. We call it like a ride share, literally. And and we will eject these satellites at the appropriate time. And it's a lot cheaper if you're trying to get multiple satellites up there to do them when they're that small. And so there's a couple other small advantages I'll talk about there is that, yes, we talked about the lower cost, but the key to me is that right now when we launch a satellite, it's using an instrument that might have been developed 10, 15 years ago. Having them, cutting down that life cycle of developing and then launching with these smaller satellites will allow us to get better instruments on orbit quicker, and that's the key to our users. So let's see. I think that's probably a good place to stop, although I'd love to answer any more questions if there are a few.
There are a couple, and I just want to point out that those videos that Tim showed today, all of them are available in their entirety on the website where you signed up for this webinar. So if you want to go back and watch them again, or if Tim went through them a little too quickly, you can see them then. Let's see. So Jack wants to know, what about the geostationary satellites? Where are their ground stations?
So the geostationary satellites that we use, first of all, the geostationary orbit, think of it as a ring around the equator, kind of like a belt, but way out there, 22,500 miles. A lot of the countries that are underneath those specific spots are controlling satellites. Like the United States has one over the East Coast and the West Coast. And that way we can see from the coast of Africa all the way to New Zealand, which is amazing. But with just 2 satellites, we can look at that space 100% of the time, nonstop. We could take images up to 30 seconds and put them together, and you basically get like high def imagery from orbit. But then the Europeans have satellites over Europe, and then the Indians and Russians, and then the Japanese, Koreans have it. So we basically have a ring of satellites around the equator that are constantly looking at imagery. And the only disadvantage to having something out there is, again, unless you have a complete ring around the Earth, you're not getting global data, and you still can't see the poles from where you are at the equator. So that's the only disadvantage, but that's why we complement them with the LEO spacecraft. But right now, we have one over each coast.
Okay, this is a good question that we always get. Carmen would like to know, what is your favorite part of your job?
You know, it has to be launch. There's nothing like a launch to get your blood going. I think it's because it's the culmination of so many years of effort. You know, you're thinking, oh my goodness, there's always a chance that something bad could go wrong, right? And so the level of excitement of being at a launch site and watching a launch is hard to describe. You can see it online, but unless you've gone down, and I know we have some people from Florida and other people that may have had the opportunity to see a launch, it's hard to describe the excitement of being at a launch. So yes, that's always going to be the highlight of my time. It's also exciting when the launch vehicle lets go of the satellite and you turn it on for the first time, but that's still not quite the same.
Yeah, I would think that would be pretty exciting. I want to point out that one of the facilities that Tim showed, our satellite, is it called the Satellite Operations Facility, NSOF? Is that what? Yeah,
that is correct.
That was the picture with the satellite discs on the roof. That's where we like drive and control the satellites. We are going to be touring that in a future webinar in March with some of the folks that work there. So we're very excited to show you that too, connected to this. A couple other questions before we run out of time here. Carl, I don't know any 8-year-olds named Carl, so I'm going to say that this might be a grown-up asking this question, but Carl wants to know, won't more satellites make it more difficult to navigate in the near Earth orbit, especially with all the current satellites and debris running around out there?
It is true that we definitely interact with the Air Force, which keeps track a lot of about all the things that are flying in the near Earth orbits. And as we get close to the potential, we look at always probabilities. When the probability gets high enough that we might actually hit another satellite, we have to move. And so yes, over time, we've seen an increase in the amount of time or the occurrences that we need to move our own satellites. But it really isn't on the scale of a couple times per year. It's not so bad. But I do worry that if a satellite hits another satellite, it creates a bunch of debris. And if you think of it, it could be like a chain reaction. So you want to avoid littering unnecessarily in orbit. You want to be good citizens of the orbit, which makes it sounds kind of corny, but you really want to be responsible. And so what we do at NOAA and at NASA, when the satellites are now when they're at the end of their life, like 15 years down the road, we have enough fuel on board to drive them back to Earth. When I say drive them back to Earth, we bring them to a place that's very remote, like the South Pacific, and they'll burn up before they hit the ocean. But we don't want to keep them in orbit forever.
Got it. And I'm told that there are children on the webinar named Carl, so I am, it was a terrible generalization to make. I guess I was making it on the way that the question was worded.
It was pretty
and so anyway, one more question all the way from Germany wants to know, how many satellites did you help build?
That's, I would say, okay, let me count. It's been about a dozen for me. I started out with the GOES satellites and focused in on I started out as a young engineer on a satellite called GOES 8, and now we're up to GOES 17, and we're about to launch GOES 18. So you can see there, that's been about 10. And then some of the low Earth orbiting ones, I've had a little less time there, but it's been about a dozen, and it never gets old, I'll tell you. If you get involved with it, you'll never get bored.
Well, it must be easy to remember them when they're all numbered, so you can remember which one you started with.
That's true.
And when is, I think you mentioned this earlier briefly, but Texas would love to know when you're launching your next satellite.
Well, we just defined a new date because of Corona. We had to move it out a couple months just because we had a little delay, but we're looking at September 30th of this coming, or of 2022. So keep your, and there'll be plenty of links that'll be on the NOAA websites and other things that we can add. But yeah, that's exciting. And I should back up. That's the satellite I'm working on. It's in September of 2022. There is a GOES satellite, the one I used to work on, is being launched this December in 2021. I forget the exact date, but I think it's December 7th or 8th. And so that's exciting too. So we've got 2 launches in the next year and a half.
And so GOES will launch from the Kennedy Space Center in Florida, and the NOAA, the polar satellite, JPSS, will launch from Vandenberg in California.
Yep.
So that was, we had to cut a slide that Tim showed a really good picture of Vandenberg and where rockets are launched. You talked about why we choose more isolated places. Do you want to talk about that quickly to wrap things up?
Yeah, when we launch from first I'll start with the Kennedy Space Center. We go east and we go over the water. So the key point is you don't want to fly over land where people are. And so we fly east, and then we basically use the Earth's rotation to give us a boost in a sense. But on the polar orbiting satellites, you want to fly south. And so Vandenberg is at a part of California that kind of juts out a little bit into the Pacific. And so when you fly south, you don't impact it. Or I mean, if there were to be an explosion or something horrible happening, then nobody would be impacted literally. So that's why we do that.
Good. Well, Texas wishes you luck.
Yeah, thank you very much.
So, well, that's all we got time for today, everybody. Thank you guys so much for watching and tuning in. Please, let other people know about it. I do want to give a little teaser for next week because we have some great webinars. We're going to be the Alaska webinar on Tuesday at 3 p.m. Eastern time is going to be about the bottom trawl surveys in Alaska and how we monitor fish and ecosystems. And then next week at this time, we're going to be talking about the Hawaiian monk seal with some folks from Hawaii. So we are very excited for that. Thank you so much, Tim, for your time, and Crystal and Trisha. And see you, everybody. Have a good week, and we'll see you next week.
Thank you so much.